Here we're going to be talking about thermal expansion. Thermal expansion happens to materials, and typically when we talk about thermal expansion, we're talking about solids, but this also holds true for liquids as well. That as an object's temperature increases, the kinetic energy of the atoms and molecules that make it up also increases. And so the example we're going to use here is for a long rod, where we had our long stick that has, these atoms in it, or molecules or whatever. They're all held together in the solid material. And as this heats up, right, the vibrations in these the vibrations of these particles will have bigger and bigger amplitudes. And so if I were to heat one side, right, this would knock into the ones next to it, which would knock into the ones next to it, and that would conduct that energy back to the left. But also as this happens, as this whole thing heats up and all of these particles are vibrating with larger amplitudes, then what happens is they all take up more space. And so then this will increase by some amount, delta L. The length of this will increase. So as the temperature increases, the amplitude of the molecular vibrations increases, which causes them to take up more space. They require more space. It's the same as if you were standing in a group of people with your arms sort of down by your sides, but then if you start swinging your arms wildly, if everybody starts doing this, you need to spread apart, or you're going to punch each other in the face, which is not ideal. You're going to take more space. When objects get hotter, when their temperature increases, the same thing happens. So for a linear expansion, right, so for our long stick where it's really this dimension and say the in and out of the screen dimension, right? These two dimensions are negligible, very small compared to the length, then really you only have to worry about expansion of length. And so that as this gets hotter, the particles take up more space, and so then it expands, it gets longer. And this delta L, this change in length, is given by this equation here. Delta L is equal to alpha. Alpha is just a constant. It depends on the material. Times L naught, that's our original length. That's this. Times our temperature change. So delta T is our temperature change, final temperature minus initial temperature. And again, alpha is called the coefficient of linear expansion, and it just depends on the material. There are tables of these in your textbooks, in the OpenStax textbook, and I will post tables from Mastering Physics on Blackboard so that you have those as well to do your homework. Now, one common application of linear expansion is a bimetallic strip, and these are used a lot in, for instance, your thermostat. So let's say you have two thin strips of metal that are made of different materials. So in this example, we have steel and brass. And because they're made of different materials, they have different thermal expansion coefficients. We have one for steel, call this alpha steel, and one for brass, call this alpha brass. And then at room temperature, they're the same length, so that this is flat. But as the temperature increases, remember that the change in length, delta L, depends on thermal expansion coefficient times the original length times our temperature change. So as the temperature increases, now at room temperature, they're at the same length, so the L naught is the same for both of them. They're glued together, the temperature change is the same for both of them. But the thermal expansion coefficients are different. So as the temperature increases, the thermal expansion coefficient of brass is bigger than steel, so the brass will expand more. Its delta L will be bigger, and that's going to cause, because they're glued together, because they are stuck together, they can't slide. It's not like you can't end up with a situation where, the brass comes out this far and the steel only comes out that far. Because they're stuck together, what that does is it causes the whole system to bend. And so then it bends up because the brass expands more than the steel. And so then what happens is, if you have, for instance, in your furnace, or in your thermostat that controls the furnace for your house or controls the air conditioner, that if we start out where they are flat, right? If this is my strip and it's flat, and let's say that I have, up here is the connection for the circuit that goes to the furnace, to the heater. And let's say down here is a connection for the circuit that goes to the air conditioner. Well, you can set this spacing dependent on temperature, because then you'll know how much this bends, or the people that build your thermostat will know how much this bends, so that you set it to the temperature you want for the furnace to come on. I'm sorry, and I did that backwards, didn't I? This one should go to the air conditioner because that's higher temperature, and this one should go to the furnace. Right? So that as the temperature increases and it gets hot, this connects, that completes the circuit for your air conditioner kicks on. But as then the temperature in the room gets cooler, this flattens back out, and the air conditioner circuit disconnects and the air conditioner turns off. Now, as it gets colder, you can set this spacing for the heater, and the colder it gets, this works backwards as well. As my temperature decreases, my length gets shorter, so you can also have a contraction as the temperature gets colder. And so as the temperature gets colder, then because the brass has a higher expansion coefficient, it's going to shrink more as well. And so then this will bend down, connects to your heater, turns on the heater, and then as it warms up, that flattens back out and disconnects the heater circuit. Now, this thermal expansion doesn't just happen in one dimension. It doesn't just happen with length. You can also have it with area. So if you have an object where, I have two, this dimension is very small, so I don't worry too much about that expansion. But this dimension and this dimension are non-negligible. So your material will expand in both dimensions. So then you're going to have a change in area, which is your final area minus your initial area. And gamma here is the coefficient of area expansion, which is just 2 times the coefficient of linear expansion, because now we're doing it in 2 dimensions. Now, an example of this is, for instance, if you get a jar out of the refrigerator and you can't open the lid, so you run it under hot water. And what happens is the lid, which is usually made of metal, will expand more than the jar, which is typically made of glass. And so then that loosens it, and now you can open the lid. And we can do the same thing for volume. So in a 3-dimensional expansion, where you have not just, where all 3 dimensions are non-negligible, then we can have volume expansion. And this is, again, a temperature change, capital letter T. Sorry for the typos. So for volume expansion, our change in volume, which again is final volume minus initial volume, is equal to beta, which is our coefficient of volume expansion, times the initial volume times my temperature change. Now for solids, we're doing this in 3 dimensions, so beta is 3 times the linear expansion coefficient. But for liquids, for fluids, beta is its own thing, because it's not meaningful to talk about length or area expansion for a liquid. It's only meaningful to talk about volume expansion for a liquid. But for solids, you can do this in 3 dimensions. Now, there are other examples of this. So, for instance, if you've ever taken a glass out of a hot dishwasher and poured a glass of water and then your glass cracks, what happens is that thermal shock from the hot glass to the cold water causes your glass to contract very quickly, and the material can't take that stress, and so it cracks. Now, Pyrex is a particular kind of glass that can take those thermal stresses because its expansion coefficient is very small. So Pyrex glass is the kind of glass that, for instance, casserole dishes are made of, or, really nice glass measuring cups are made of Pyrex glass. So you can go straight from hot liquids to cold liquids, from the stove to the refrigerator or whatever, and they can take those thermal stresses. Now, another example of this is sea level rise. So when we talk about global warming, and we have already talked a little bit about global warming and greenhouse effect, but as that happens, the sea levels are also rising. Now, the reason that the sea levels are rising is a little bit because of melting ice. But it's mostly not from melting ice, because it turns out that when ice is floating on water, and then if the ice melts, the water level doesn't change because of the way the buoyancy works. And most of the ice that is on the Earth's surface is floating ice. There is, of course, Antarctica, which is not floating ice, and if that melts, that will cause some sea level rise, but not really enough given the immense volume of the oceans. The bigger problem is that as water gets warmer, as the oceans get warmer, water takes up more space. And the only place for it to go, because the actual ocean basins have a set size, those aren't going to expand nearly as much as the water does. The only place for the water to go is up. And so then the sea levels rise. And we're seeing this now in places where, southern Florida, where it's flooding in the last 10 years, way more than the previous 100 years. Small island nations, New Orleans, lots of places where sea level rise is impacting sort of daily life in these places. When we talk about thermal expansion, that as materials get warmer, their density decreases because they take up more space, they get larger for the same amount of mass. And that as they cool down, their density increases because they take up less space, the same mass is concentrated in less space. And for most materials, this does hold true. But there are some exceptions, and water is the most common of these exceptions. So for water, liquid water behaves normally. Ice behaves normally. But around the phase change, it turns out that ice, even though ice is colder than liquid water, it is less dense than liquid water. So it turns out that particularly for water, that as water increases, the temperature increases from 0 degrees Celsius to about 4 degrees Celsius, water's density decreases. Water's density increases. The size of it decreases. Water actually contracts and takes up less space just in this particular temperature range. Now, above 4 degrees Celsius, water behaves as you would expect. And below 0 degrees Celsius, ice behaves as you would expect. But it turns out, though, that the density of ice is less than the density of liquid water. And so that's why ice floats. Whereas for most materials, the solid version of that material sinks compared to the liquid, right? That the solid is more dense than the liquid for that particular material. Whereas water, the solid phase, ice, is less dense. And this is why ice floats. So that's it for thermal expansion. Next time we will start talking about energy transfer. How do we get heat energy from one place to another place, and then kinetic theory and our laws of thermodynamics.